Next, we have Professor Mark Fišel from our institute, Professor of Natural Language Processing. So he does all kinds of applications with the techniques that Mark was also showing. So Mark did his PhD here in Estonia, postdoc in Switzerland, and we are happy to have him back as a professor. When he got professorship, he was at that time the youngest professor of the university when he got his position. So please, Mark, the floor is yours.
Thank you, Jaak, for the warm intro. You can see my slides. Can you hear me from the mic? Good. My goal today is to keep you awake enough after lunch, and I will continue the NLP topic after Marek. Marek focused on encoders. We made an agreement that he will cover encoders, I will cover decoders. I wanted a fancy show-offy title, so I wrote Learning to Write Text Artificially, but only after that I realized that the title itself is a very good excuse to show you what kind of material we're working with. So language, unlike image data or any kind of other data, it is peculiar in many ways. So if we look at this phrase, learning to write text artificially, many of you maybe thought it's going to be an inspirational talk about writing artificial texts. So to learning to write text artificially. So we can show this variant of interpreting the sentence by attaching this adverb artificially to the verb write. And this is obviously not what I meant. I rather meant artificially learning to write the text or using machine learning to create models that will generate text or write text. So this shows us that language is an exciting kind of material and modality or data kind to work with, and one reason behind this excitement and difficulty with working is it is because the language exhibits ambiguity on so many different levels. So one and the same word can have different meanings, one and the same phrase can be interpreted in several ways, and so that's what makes it hard and exciting. So my plan is to try and fit into 45 minutes. My plan is to tell you, first of all, the motivation behind decoders and what they are used for. Then I'll try to basically do a very soft and nice introduction to transformers used for decoding purposes, and this will cover mostly GPT, so generative pre-trained transformer kind of models like GPT-2, GPT-3. Thanks to the OpenAI and Elon Musk's efforts, this has been PR'd much more than encoder models, even though in NLP, I think encoder models are used even more, or at least are no less important than decoders. I'll talk about those. I hope I included a couple of slides about why this is not general AI, even though some of the results are impressive and some of the news releases do leave a wow impression, but let's see. GPT, and then I will also tell about encoder and decoder combinations in tasks like machine translation. So if I have enough time, I'll cover our work as well, or at least briefly look over what we are working with. Marek told you about this part of NLP, so natural language processing, which is encoders, the goal of which is to learn to, so to say, process or read or understand text, like sentences or any kind of other segments, and learn to find out something about this segment or this text. So a text segment goes in, and then we can either classify it according to sentiment, positive, negative, neutral or polar or not, or spam or not spam, or any kind of other classification, or decide anything about the words in the text segment, like, for example, they're parts of speech. So whether each word is a noun, a verb, an adjective, an adverb, or so on, or decide on whether this whether this word is erroneous in the sentence, like Marek showed. And there are many other ways of using encoders, and in the end, what they do is they learn contextual embeddings or vectors to be paired with each word or each token in the sentence, and they then can be either used directly in some applications or fine-tuned together with additional parts of the model. So decoders, unlike encoders, they don't produce nominal output for words or text, they produce text, new text. So decoders are meant to learn to generate new text, new segments or new documents. Theoretically, this can be applied in the way that we have some kind of data, which is structured data, and we turn that into coherent and fluent text that explains us this data. For example, date, yesterday, destination, London, and air company Lufthansa. So, and this can be turned into the sentence like, yesterday I took a Lufthansa flight to London. We can also generate text based on prompts or prefixes. So we have a beginning of a sentence and we can ask the model to continue this sentence, and I will focus more on this part of stuff. Then we can of course generate text based on other text. So we have some kind of text input, like when we're translating or when we're paraphrasing or when we're simplifying or summarizing. And of course, there have been several attempts at doing automatic captioning. So we have an image and we have to generate a text that describes that image. So lately there have been a lot of fuss about DALL-E 2 and those kinds of models which do the opposite direction. You take text and you generate an image based off that. A very useful thing is to do it based off images and to generate text, like to describe images for visually impaired people, for indexing on the web, and so on. The motivation behind doing this, first of all, is doing tasks which are done by humans and automating them or speeding them up. So machine translation is one. There are millions and millions of segments and hundreds of thousands of documents regularly being translated for EU purposes, for localization purposes, for software, for all kinds of other purposes, and speeding this up or automating the more boring parts, the easier parts of this, is of commercial interest. Also, this example here, I think, is a very nice way of, again, emphasizing the beauty and the complexity behind language. So this translation example here, in Estonian, it literally says there is no error. And in English, it's okay. And this pole viga doesn't necessarily mean that there are no errors. It's this Estonian way of reacting. It's this Estonian way of expressing positive sentiment. Instead of saying this is great or this is awesome, you say it's normal or it's okay. There's nothing wrong with it. So and also translation isn't supposed to be done literally, neither by words nor literally according to phrases out of context. So we can easily imagine a movie with a subtitle where even though it's okay is not a direct translation of the phrase pole viga, but in that context it will be a completely appropriate thing to say in that movie. If in Estonian the phrase was pole viga and in English it will be it's okay. So that makes the task of translating also challenging and nice and exciting. Then another application of text-to-text transformations, or they're also called sequence-to-sequence transformations, which is applied more broadly than text, is text simplification. So I'm borrowing this example from Richard Feynman's autobiographic book, Surely You're Joking, Mr. Feynman. Feynman writes that he at some point tried to read sociology materials or, let's say, expand his boundaries of knowledge, and so he was a physicist, the Nobel Prize received, so Nobel Prize nominee, and he tried to learn something about sociology. He tried to read some materials given for some seminar, and then he realized that he's just reading text without comprehending it, just reading and then doesn't remember anything about it. So he stopped for a moment and decided, I will just translate this into simpler language for myself, or translate into what this means. So the first sentence he read, and he quotes, is, the individual member of the social community often receives his information via visual symbolic channels. And he thought a little bit and realized that all this means is people read. We might have a use for automatic simplification if the texts are, let's say, highly scientific or very domain specific, or let's say there are banking texts which explain to you some interest rates and something about loans and so on, and you want it simplified so that you can understand it quickly and correctly. There is also summarization, so long text into shorter text and so on. Another motivation is this GPT-3, and I'll now try to focus on that, which is a purely taken standalone decoder without anything else added to it, and then we'll come back to translation and text-to-text. What GPT-3 and what decoders do is a very simple task we humans can solve usually very easily. So if we have a partial sentence, we can predict the next word. If we have a sentence like, would you like tea or beer, right? Or coffee or something. We can predict the most likely next word. We can also predict the set of words which can appear there, and we can most likely also determine the words which are very unlikely to be there. Would you like tea or to get killed is grammatically correct, but probably you wouldn't expect to see it. Would you like tea or mud is even worse, but still grammatically correct. So we have a clear idea of what is likely to follow these words and what isn't. So then if we take a lot of texts of sentences and we train a neural model based on those texts, we can hope that this model will be also good at predicting the one next word. Why would we want to do that? I mean, this was maybe a fun example, but why would we want a model that generates one next word? So this can be used to generate text from scratch. So taking a part of the sentence and just predicting the next bit is called autoregressive text generation. Why autoregressive? Because we can generate part of a sentence and then pretend that that part was already there, and we will condition the next outputs on that part of a sentence. And then whatever we have generated, we will add to the already existing part and then condition on that and predict the next word. So we can predict based on only the fact that there is an empty sentence, we can generate a random word. It's not going to be a random pick from the vocabulary. It's going to be a model's prediction on what is likely to start a sentence. For example, the word this. Now, next step is we use the same model and we do those steps separately. So we already predicted the first word will be this. Now, knowing that the sentence begins with the word this, what could be the next word? And we can then, for example, randomly generate the word is. What we actually do is we don't pick one word that can appear there. Obviously, a sentence can start with several other words. We estimate the probabilistic distribution of which words could follow. So in the beginning of a sentence, the distribution will be quite flat, and there will be a lot of words that can begin a sentence with tiny or but similar probabilities. Here, this is can be continued in several ways, like this is a something, or this is the way, or this is weird, or this is it, or this is my, or this is something. We estimate this probabilistic distribution over the whole vocabulary, and then we can pick the most likely one or randomly sample according to this distribution or do anything else with it. That way we can theoretically generate a random sentence. Like, for example, this is a short example. It's a constructed example of I have never seen a single GPT model generate that particular sentence, unfortunately. The applications of this kind of text generation are not only to replace lorem ipsum in web developing and generating random texts. Oh, by the way, yeah, we can generate text and we need to stop at some point. And we just train this with segments ending with an end of segment. And once it has generated the token end of segment, then then we know to stop. So the applications of this kind of trained model are numerous. First of all, we can evaluate the likelihood of a given text. If we have several hypotheses of texts, for example, we have several translation systems or several other text generating systems, and we need to evaluate those different options and pick the best one, we can use a GPT-like model or a decoder-like model to compute the probability of the whole sentence taken together. So the probability of the sentence, this is a short example, will then be the probability of this times the probability of is given this times probability of a given this is, and so on. But that relies, of course, on something else that generates the text, so we evaluate and pick from there. Another application is taking a prefix or a prompt and then auto-completing the text. we can think of several funny ways of generating text and see what the models think about, but there, and I won't start doing a live demo here, but you can go to this Hugging Face link here that can be used as an online demo and just play around with text, basically. For example, just to show you what it does with text generation, when making the slides, I entered the prompt, and you can hopefully see it with, here it is, black until here. So the text in black is what I wrote in there. Tartu is a great place for a computer science summer school because everything else is what the model generated. Because it is a small, informal, and open to groups. It is small, informal, and open to groups with friends and families. It obviously doesn't know what Tartu is. But it knows it's maybe some place or maybe some venue, so it generates some text that could describe something related to holding summer schools. Students are free to do some of the most, this is why I included the example. I like the students are free to do some of the most common computer science related activities like the web, reading, and so on. So, nice description. I wasn't satisfied with this, so I entered as for escas, I think that, and then, so I begin the generation with a prompt, so that I guide the model to sort of express a thought. It's not really thinking. I mean, all it does is generate random text, but because it's complex enough to see the whole text structure, and it ties together the sentences and the meaning and everything. So here is the stop of my prompt. So as for escas, I think that, and everything else is what the model wrote. This is a good start, but I'm looking forward to hearing more on the topic. I think escas is a good idea, and I too think that it will be hard to get enough support for it. I think the main problem is that many organizations only want to work on one product at a time. I mean, here it makes no sense. It doesn't know what escas is, even less than Tartu, but you can see that this text has structure. So it's not a bunch of random sentences, it's not a bunch of random words. This is a randomly generated coherent text. And it's semi-believable that a person could be saying that, and I don't know, maybe somebody who wants to produce an impression that they know what they're talking about without knowing what they're talking about could exactly sound like that. So this, the model pulls off. This completing of prompts actually has very nice and surprising applications which were published in the original papers of GPT models, so GPT-2, GPT-3. I think GPT-2 was originally titled Language Models Are Unsupervised Language Learners, or something like that. So if we write a question followed by the word answer, colon, and then let the model generate, then we can hope that it actually gives an answer. I didn't include the, I have another screenshot of is Tartu the capital of Estonia? Answer, and then it says, although it would be very desirable, but unfortunately Tallinn is still the capital, although Tartu was the capital right after World War II, something, 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 so I don't know where it took that from. Here, if I ask it, where do I buy weed in Tartu? The answer is, at first, it seems like it just doesn't know what it's talking about, because obviously you buy it in other places. We have listed the best pharmacies selling weed in Tartu, order your weed online, but then you see that it immediately switched into clickbait mode. So it just repeats my question, like where to buy weed in Tartu, weed and marijuana, where do you get it, and so on. Why? Well, because this model learned on texts from the internet. So it saw a lot of texts on the internet written by people, and there was probably a lot of clickbait. It didn't learn particular questions about weed and Tartu. I haven't seen many texts about weed and Tartu, but it has learned, it has generalized enough to see that there is a question and you can just repeat it and also discuss it, and it knows that weed can go with pharmacies and so on. So it's pretty dumb, but it's pretty smart. There is also a few-shot or a one-shot application of those generative models. And let me remind you, so even though it seems like this is an uber-smart model, we just showed it a bunch of unannotated texts. I mean, all it saw during training was how to generate the next word. For that, it saw billions and billions of sentence examples from the internet. And now it learned to answer questions and maybe even translate. So if we write translate English to German, colon, a small table, it doesn't cope with this one. It sometimes copes with other examples, but it even manages to translate, but not in this case. Why not? I mean, why does it cope with translation without having seen any annotated examples of input and output translations? Well, I mean, it has seen a lot of texts, and nobody filtered them 100% to just English. Sometimes texts are vocabularies or phrase books where you have translations in there, so it can learn that kind of a behavior. Not just memorize the phrases, but actually translate, even though it does worse than the actual translation systems. So doing this, and my prompt stopped here. So I didn't show it any right examples. I just wrote to it, translate English to German and a small table. I was wondering if it would say Tisch or Tabelle, so a table like this, or a table like a matrix of numbers, but it failed to translate. That would have been 0 shot. 1 shot means that I don't retrain the model, I still use the trained model like this, but I stop the prompt here. So I give it a task written in text, so translate English to German on the top there, and then I show it what I'm expecting of it. So a small table translated into ein kleiner Tisch, and then I ask, a big surprise, and now please translate, hoping that the model, when prompted or prefixed with this correct example of a translation, would understand better what is expected of it. So you can do 1 shot or you can do few shot applications where you show several examples, but not really many, but let's say 2, 3, 10 or so on, and then ask for an output. And here you can see that a big surprise was correctly translated into eine große Überraschung, and a big dinner. My German is limited, but I don't think eine große Dose is a dinner. But the first phrase was successful, but since it learned to generate text, then you see it does its best to continue and generate text. So after the translations, it tried to, in a small town, blah, blah, something. These applications are astounding and sometimes can lead you to think that the model has learned the language and now can just look at text and speak it, but in the end, it only generates the next text. It only repeats this behavior because it has seen that in the data. How is this done? First of all, so how do we train a model to do it? How do decoders work? They work via training neural nets to estimate probability. So in the end, this is only a smart way of estimating probability of the next word. So we take the prefix, like would you like some, and this is the condition on which we are generating. And so conditioned on words from 1 to, let's say, I-1, we generate the probability, or we estimate the probability distribution over the whole vocabulary of the next word. So here, and I mean, this is constructed. Usually those probabilities are much lower and the list is way longer, but let's say, would you like some could be continued as, would you like some tea? Would you like some food? Would you like some advice? Would you like some sugar with that? And so on. So for each entry in the vocabulary, like here, we assign some probability. The sum of them will be 1. So in that sense, this neural net, all it does is read the text somehow, and do some operations with it, and then produce a probabilistic distribution. But the complexity behind it is what allows the model to see the whole text and to tie the sentences coherently together so that, I mean, we could estimate the same probability with the usual maximum likelihood estimation, making the Markov assumption and, let's say, looking at the 3 last words, or picking some random words out of there, or doing something else. But so far it seems that the neural nets with transformers or with RNN encoders or decoders seem to be doing the best job so far, as Marek said. So almost any models now working at the state-of-the-art level will be based on transformers, or a hybrid of transformers and something and something. How do we actually do it? So Marek covered this part. Just in case, a reminder. So if there is an encoder I mean, I will slightly repeat this part purely because decoders are essentially the same thing as encoders. They're the same kind of a transformer model. They're just trained and applied differently. We still have the same procedure, and you can see I'm also using pictures from Illustrator Transformer, which is linked here below, and a very nice and easy way of learning about transformers. There's one on BERT, there's one on the original transformers, which were encoders and decoders, and a lot of other materials there. But so we'll start with two words here in this example. So thinking machines, they will get replaced with their fixed embeddings, like Word2Vec used to do here, the embedding x1 and x2, and then they will get their keys and values and queries and other vectors which enable the self-attention part of this, so that each word gets a representation vector z, which is a weighted combination of value vectors from each other word in the sentence. So by the way, I have no explanation why they did it like that. So why didn't they do attention in a different way? Why exactly queries, keys, and vectors? Why not just queries, keys, and values? Why not do 2 vectors or 4 vectors? And I don't think anybody has a non-philosophical answer to this, but maybe to be discussed later. So we take the input text, we compute self-attention between all of the tokens in there, so which makes self-attention quadratic. So for each word, we do a weighted sum of every other word in the sentence. And so we repeat that for each word in the sentence. So the complexity of this thing is quadratic relative to the length of the sentence. As you can see on the left, we do this in multiple steps. So there are multiple encoders in this network. So the minimal size, or the typical size for a base model, is usually 6 encoder layers. Experiments have gone up to 1,000. Usually it's more like 12 or 24. Some smaller distilled models have used less. And there was before, I think, a question from Ike, what do we use to initialize the vectors in between? And the answer is we don't. So all of this is an end-to-end learning scenario where we define a really complex computational path or computational graph where words get embeddings, generate queries, keys, and values. Those contribute to self-attention. This is done multiple times. This is passed through feed-forward layers with additional signals from somewhere, added to positional and other embeddings, and then in the end trained to produce this one answer, and all of those just learn without any kind of intermediate supervision. These are encoders. Now, the only difference between encoders and decoders is in how they are trained. So if an encoder is pre-trained, this is not multi-level marketing, this is masked language modeling, just in case. So the masked language model training means that we pick 15% random tokens to maybe mask and maybe not mask and maybe replace with another word. Getting an input like this mask a test, and the output for the model to learn to produce this is a test. So this is an encoder. It gets a whole segment, a whole sentence, and tries to restore words that were masked. Then a decoder is absolutely the same kind of a transformer without any kind of mathematical difference, except where we pass it partial sentences as well. So like empty or this is and something, and we train it to predict the next word in the sentence. So only the last word is masked, and then we train the decoder to predict, to restore this mask only at the end of the partial sentence. Other than that, it's the same kind of a transformer, and it can be done with the BERT kind of approach or Roberta kind of approach with intermediate tokens, additional tokens, or positional embeddings, no positional embeddings, language embeddings, no language embeddings, and so on. Now, to sum up this story, the first and the main stage in creating such a model like GPT-3 or any kind of other decoder, which is not conditioned on anything else, which just generates texts, is to collect billions or as many as we can segments or examples of text on which it will learn, and then train the decoder on it. For English, there are billions and hundreds of billions of segments available to train such models. For Estonian, when we trained the Estonian GPT back in December, we had 2.2, I think, billion words. After that, the newer version of the Estonian national corpus was released, and this now includes 2.9 billion words, so not segments. So I imagine this is less than 1 billion sentences. And so this is not so much, but then again, this is quite a lot, so the models learn with this quite nicely. Based on this material, which is only text, no annotations, no information about the text, it's just running text, the decoder learns to generate some more text. And you can say that it sort of learns the language, because it learns, it generalizes what it has seen, it can perform in a zero-shot manner, one-shot manner, and so on. And it's beautiful and it's useful. However, this requires huge resources. So months on several GPUs is probably a typical requirement for training such models. If we go for bigger models, then hundreds and hundreds of GPUs will be required, and those models can easily cost millions of euros and more. Now, let me stress this, and I cannot stress this enough, and this is the main part of the talk. If there's one thing you remember about these models, it's the following. So thankfully, thanks to Hugging Face and other repositories, those pre-trained models created by big companies are made available to others, and you can take this pre-trained model, so it was pre-trained in an unsupervised manner on raw text, and then you can take it and continue training it. Why would you do it? It's called transfer learning. So you essentially take a model that was trained to perform one task, which was to continue a sentence on a bunch of general texts, and then you continue training that model on a narrower task. For instance, if I want a random text generator, but I specifically want to generate not just generic text, but I want to generate random SCAS promo emails. All I need to do is take a pre-trained GPT-3 or GPT-2 or one of the GPT models, collect from my inbox all the promo emails sent by our institute from the 19 previous SCAS summer schools, fine-tune the model on these emails, and it will learn to generate random SCAS promo emails. Why don't I do it from scratch? Why don't I just start training with those emails? Well, because there will be maybe a couple of hundred of them at most, and this is way little material for a model of this capacity to learn. On the other hand, if we pre-train the model on general text, it starts not from scratch, not from a random state, but it starts from knowing the language in general, and then during the fine-tuning, during continued training, it learns to focus on a particular domain of interest. Another way of using pre-training and fine-tuning with decoders is to pre-train a decoder on several languages, let's say 100 languages, and there are models on Hugging Face available which have been pre-trained as a decoder on 100 languages or so, and one is XGLM, so X stands for Cross-Lingual Generative Language Model. And let's say we are interested in a tiny language. Estonian isn't tiny anymore, but still, we can take XGLM and fine-tune it on a single language so that maybe it benefits from having seen Finnish or any kind of other Finno-Ugric languages, or maybe even English and others where in Estonian you take some names or share some other similarities with other languages. Probably not Hungarian, it's too distant, but maybe the overall logic of longer sentences turn into longer sentences, or how sentences behave. So this means that even though pre-training a model costs a lot, you don't need to do it, most likely, unless you have a good reason to do it. Because you can, unless you're working on a better way of pre-training a model, then you can just take an existing model and tune it to your own purposes. So let's say if you're interested in practical NLP applications, then it's most likely that you can take an available model, tune it to your purposes, and that will cost you a couple of days of GPU time, not more. depending on the size of model, size of data, and of course, several other factors. So why is this great? Why is this awesome? The specific final tasks that we want to solve, they rarely have abundant data. Like everyone in the world who has ever wanted to generate random SCAS promo emails probably has very few material for that. If we are focused on only medical text generation, it's much easier to collect a small amount of data for medical text and then tune a model on that instead of collecting millions and billions of documents and then training a model from scratch on that. So the transfer learning from one task into another, from one domain into another, guarantees that this can be done. And this is much less resource heavy, so this can be done much more cheaply. Practical pointers are all to Hugging Face. I mean, the GPT-3 isn't public. GPT-2 is. There's also this startup called Eleuther AI, which have been training bigger and bigger models. So there's a GPT Neo 1.3 billion parameters, GPT Neo 2.7. Now there's a GPT Neo X. So they try to replicate the original GPT-3, but with an open source and openly accessible model so that it can be taken from Hugging Face and used for whatever purposes. And for Estonian, we have done our share of contributing. So there is this GPT for Estonian. It's not GPT-4, but it's GPT for Estonian. There's base and large. And colleagues of ours have also trained Estonian BERT. There is, I don't think Estonian fine-tuned Roberta is public yet, but it eventually will be. And so Hugging Face is a very nice code repository. So it's essentially a GitLab, which also has a Python library so that you can directly import those models into Python with a couple of rows of code. And it's also an online demo for testing out the models. So you can open any of those links and test the models in practice and see text like the ones I had on screenshots. These can be also fine-tuned from the same code repository and so on. So this is very useful to do any kind of research or development. Now, I have 8 minutes, 50 seconds on the timer. Let's talk also about combinations of encoders and decoders. So a decoder was just generating random text, and despite that, we found some useful applications to that. How about supervised training of, let's say, translation or simplification or anything like that? Of course, we can squish the input and the output into a single segment and then just train a decoder and give it the input sentence as a prefix and then let generate the output. But for reasons that are partially mystical and partially not so mystical, it's better to take something that is meant to read text, which is an encoder. So it's meant to take text and to turn it into meaningful, in its own way, contextual representations, and then use a decoder to generate a text in the other language. So we will take the encoder like BERT here, which will have the self-attention and all the shortcut connections and everything else and so on, and multiple layers of the encoder. We will use it to represent the input text, which here in this example, also borrowed from the illustrator transformer, is Je suis étudiant. We will represent it with contextual vectors that it computes, and then modify the decoder that we've seen so far with GPT-2, so that it sees, via self-attention, its own partially generated output first, and also the contextual representation of the input sentence second. So when the decoder generates the output, I am a student, autoregressively, so it starts by generating the first word, I. For that, it sees that the input is Je suis étudiant, and the output is empty. What's the first word? It says I. Now, the next question. Input, Je suis étudiant, the output is I. What's the next word? It generates am, and then a student. And I think I even have an animation of it somewhere there. The decoder is, in this case, is almost the same kind of a transformer as the encoder, except for this encoder to decoder attention added there. So there is the self-attention for processing the partially produced output, and there is this encoder-decoder attention, which brings weighted combinations of contextual representations of the input, not of the output, into generating the output. In the end, if we generate a sentence like the one we saw before, would you like tea or something, this time from Latvian. So we have the input, vai jūs gribat tēju vai kafiju. Now it's coffee, not beer, unfortunately. What we estimate now with this encoder-decoder transformer is the probability of the next word, of the next output word, so WO, number I, assuming we've already generated the output words from 1 to I minus 1 here, and this is in the beginning, it's empty, and also the full input. So words on the input from 1 until, it should be the end of the sequence, not I minus 1, of course, my typo. It's the whole input, I just didn't want to include all of it here. So vai jūs gribat until the end. Essentially, we're estimating the probability of the next word given the previous words in the output and all of the words in the input. But we do this through replacing input words with vectors and doing all the self-attention and decoder attention and so on, so that we end up at this softmax or probabilistic estimate of what the next word should be. And what we do with this is generate one word at a time, would, you, and so on, like tea or coffee, and wait for the decoder to generate the end of segment symbol so that we know that we need to stop. Do we need to stop?
I don't want you to steal the time from student presentations.
Okay, then thanks. I'll skip a lot of sexy stuff, but I wouldn't want to steal time from students. Work I have been talking about, of course, is based on the work of my team, and there's a lot of missing pics from here, partially because it's a small slide and partially because they didn't give pics, and I'll just give you a message to take home. So decoders like GPT-3, they learn something very simple, predicting the next word from raw text, but this results in some useful applications. And the best thing about it is transfer learning, so we can pre-train and then fine-tune a model to do something specific. And so in the end, for practical applications, you must have a really good reason to repeat pre-training and not reuse the existing stuff. So thanks, and I don't know if we have any time for questions.
Experienced professor did not want to get any questions. Any questions?
Your clock is off, 2:15. Says my synchronized clock, so I'm precisely on time.
I have one very small question. Basically, I just wonder if there has been any studies about transfer learning within language families, you know, like how does it work in Indo-European languages and Finno-Ugric languages, etc.?
Yes, there have been, and it shows mainly that related languages help much more than unrelated languages, even though the unrelated ones help. But I can give you a much longer answer if you're interested after offline.
Okay, thanks.
Sure. Thank you. Let's thank Mark.